My name is CJ. I'm from Newman Engineering. Welcome to our this short course about the modeling of reinforced concrete using midasNFX. So in this topic, basically we will be focusing on the RC buildings with this seismic load for the earthquake analysis. As being mentioned, the main objective of this course is actually to study the seismic response on reinforced concrete building under the seismic load. As you can see, the overall idea of the structural system building is being implemented using midasNFX by utilizing the 1D and also the 2D elements. Both of these elements will be reconstructing the whole system building for seismic loads, and we at the end of the result we will be seeing how the response due to the seismic load implemented. The reinforced concrete building floor plans and longitudinal section is being shown here. The floor plan has a width of 156 feet by 66 feet. The overall floor that we have for this reinforced concrete building is 12 floor plus with the roof. Okay, let's get started with the courses with my latest midasNFX 2020. And for those who is not familiar with midasNFX, so I would like to take this opportunity to make some introductions. Alright, so we have the graphical user interface of midasNFX, and you can see on the top basically we have a few tabs that enable you to make the modeling for either FEA analysis or CFD analysis. So throughout this tab, you are able to set up your own case study in the FEA boundary condition, which is the static heat analysis and dynamic transient heat analysis. And in the same time, we have also the CFD setup. All right. So on the left panel, this is the quake access panel, the QAP. The model will be displayed here if you start with the new sheet. Let's start with the new sheet. Okay, so a project has been initiated, and please note that the unit system by default is utilizing the Newton as the unit, the mm, the joule, and the second. So if the user do not prefer to have such a unit, and we can change it here, or we can change it on the right bottom. So in our case study, we'll be focusing on using the feet and inch. So we prefer to use the feet and the pound as well in this case. So again, back to the QAP, the Quake Access Panel, we have the model. The model means that this is where you keep your materials, where you keep the properties, where you keep also your geometricals. Right, and also the mesh that has been generated as well. The second tab goes to the boundary conditions, whether you have the FEA boundary conditions and you have also the CFD boundary conditions. And the last tab visualize the calculated results output, where you can post-process the results here. At the top tab, we are having a geometry tab, which you enable to do the 3D model by using this preprocessor of midasNFX. This is one of the options you can try. You can also import from your external CAD tools, right? So the CAD that are acceptable, so for example, like CATIA's for version 4 and 5. If you are using SolidWorks, Unigraphic, Inventor, Solid Edge, of course you are able to import the AutoCAD drawing as well. Definitely we do have a universal file format like Parasolid, ski file format, step, and adjust. So let's say if you have the AutoCAD, we can use this function to import the DXF file, whether it is in your 2D wireframe or 3D wireframe. All right, let's go into the modeling, the mesh modeling. You in the tab of the mesh, you are able to create the 1D, 2D, and 3D mesh. Of course, as a professional user of the finite element or CFT, you will be able to manipulate the mesh that you have created, either by accessing to the nodes modification or the element modification as well. Of course, the mesh that you created, it can be extruded, it can be filled, it can be swept, it can be projected as well. On the other hand, you may also make the mirror of your mesh translate or rotate. In FEA analysis, we have both the static and transient analysis. So this is where you set up your boundary condition of static analysis, and this is the boundary condition you set up for your transient analysis. So in our case study today, we'll be focusing on the spectral response, and of course we'll be using a dynamic load set. So on the other hand, the other solver that we have in is computational fluid dynamics, the CFD, where you can set up your inlet, outlet. You can do for multiphysics like conjugate heat transfer, the porous medium. You can run on the multi-phase. You can have so-called the multi-species analysis as well. The next step shows you the analysis where you are ready to run your analysis case, and the last step shows the post-processing tools that you may be able to utilize to see your result, to tabulate your result, and you can also export the grid result into the Excel, the text file, and etc. Okay guys, let's start with our project. We will be creating the modeling within the preprocessor of midasNFX. First of all, let's align our grid into the top view. The second is we are going to use the unit feet. So make sure that you have selected feet in order to create the model. Alright, so since that we will be starting the layout of this floor plan with the dimension of 182 feet by 66 feet. So we will be creating a rectangular, a 2D rectangular, and let's select the first point, and the dimension that we are going to build is 182 feet by 66, right? So we don't need actually the face, so let's just deactivate, and we'll be able to see our model. So let's turn off our grid and the guideline, and let's make the full zoom there where you are going to have your floor plan according to our objective today. So the second part is that you may notice that the grid unit that we are using is not appropriate, is too small in our case study, so we will have to adjust the grid unit. Let's go to the define grid. As you can see, we have 0.06 feet, and let's make it a little bit bigger, say for example 5 feet, and preview. Oh, this is good, and we need to have more, so let's create more, let's say 50. All right, so in order to have a good coverage, okay, let's accept OK. Okay, so now what we are going to do is, since that we are going to have the floor plan in the for each column with the different dimension, for the internal column, basically what we are going to do is we are going to copy each of the edge towards to this direction, and the edge towards to these directions. So as you'll notice from here, this is actually the curve that has been created in the form of wires. So if I select the whole wire, so means that if I make a copy, then it will copy the whole wire. So this is not what we want. So we want to have individual edge. So we will be using the explode into the edge from the wire here. So we don't need the wire actually. So just delete the original, and we are going to have each individual wire created. The next part is we are going to make a translation into this 26 feet. Let's make the translation into the this X direction. We're going to have 26 feet, right? Yes, 26 feet. So makes a preview. Well, this is far. I think I have selected here, yes. So let's do it here. Okay, so this is what we are going to have. We are going to have repetition 1, 2, 3, 4, 5, and 6. Let's put it 6 and make the preview. Yes, we have the repeated edge is created. Let's make apply, and we want to have this edge created as well, and we are going to translate along the y negative direction. So this is the y direction. Make sure you have copy. All right, and the distance we are going to apply is 22 feet at 2 times. Let's make it 2 and preview. Oops, it has to be a negative value. Here you are. All right, so let's make OK. Then we have the model about to ready. All right, the second thing is that we will have to create the individual beams, all right, at the end of our project. So but the beam is not crossed over with this original beam. What I will have to do is I just make intersection, select everything so that each of the beams has been divided accordingly. Okay, so the next thing is we will have to prepare some materials before I can actually do the remodeling. So let's add some materials from our database. In my case, I would like to use the ESTM for the reinforced concrete. Yes, these are all the preset value. Here you are. And in our case, we are going to have the edge column. We are going to have the edge column will be at the edge here, all right, and we're gonna have an interior column in the interior part, and we're going to have beam as well, and we're also going to have wall. All right, so first let's create the internal the edge column. Okay, let's name this one as edge column, and let's build the sections. So the edge column is built by the bar section, and we're gonna have this dimension 24 by 24 inch. And make sure you have selected the right materials. Let's apply. Then we're gonna have interior columns. Let's go to sections, bar. So the dimension of our interior column is 30 by 30 inch. Oh, this is inch, yes. So yep, you have to do something else first. Let's move to inch. Right, so let's make some modification which we have done before. All right, so this is 288, so no, this is 24 by 24. Right, so don't worry if you have selected the wrong unit, and you can actually change back to different units after you have set up, but just to make sure that the value that you have already keyed in is reflected to the one that you want. Alright, so we'll proceed. The second part is the interior column. So in the interior column, we're gonna define again our dimension of the bar. Interior column is going to have 30 by 30 inch. Okay, and we're gonna have, last but not least, the beam, and we're going to use the section as well, the same, and the beam is having 20 by 24 inch. Okay, so we are actually preparing, so we are not yet apply the properties into our the model yet. So we are going to prepare another wall. All right, so using the membrane, and make sure that you have selected the right materials. Let's name it as, we are going to have wall, yes, of course, and the thickness of the wall is 18 inch. There you are. So these are the properties that we have created. So the next part is we will make the real beam and the column right away. So first is we are going to create the beam. All right, so in our case, we are not going to have this beam, which will be replaced by the wall. And let's delete this. All right, so we will create the wall after that by using this 2D wall. So first, let's create the beam first. Using the mesh tools, the 1D mesh, we are going to select everything. And okay, I'm going to have one division in this case. Make sure you have selected the beam properties here. Okay, let's name it as the beam. So these are the beam that you have just created. All right, so what about the column? All right, so we are gonna have two type of column here, the edge column and the interior column. So the next thing that I can do is, let's align properly into the top view. Let's create the edge column. All right, the edge column is using the extrude features. We're going to extrude each of the edge nodes here to create the column. So what I'm going to do is, first, to make things easy, I'm selecting everything. So you can see that the node has been selected and is been highlighted in red color. However, this point, interior point, I will be assigning to the interior edge. So what I have to do is, I don't need this for the moment, so I just deselect using the deselect tools here. All right, so I'm going to extrude this point into the Z direction, and here I have 16 feet. All right, so yes, feet, let's go to feet. Nice, we have 16 feet, which is in the minus direction of the Z here, and this is the edge column. All right, so let's make the name of edge column. Oops, yeah, of course, we have to realign the coordinate system of that particular extrusion, and you should be able to preview the edge column. So now we are going to create the internal column here, using the same method by extrude the nodes into 1D. We'll select this, the direction. This is the coordinate system, so don't worry about that. Okay, so the most important thing is where the direction of the node will be extruded into the Z direction. We'll be using the same dimension, 16 feet. And this is the edge column. Let's rename to the edge column. Preview. All right, so it has to be a negative value. Okay, then just turn on all the edges, you'll be able to see the real structure. Okay, now let's create the 2D wall. Alright, this is 2D, we'll be using the wall, and we have two walls actually. Okay, let's name this one. No, actually I have to create the I have to create the elements, right? I have to create the 2D elements. So we are working in the environment of the mesh here, so we are not working directly with the geometry. Well, yes, you can do that by creating the surface. You can creating the so-called the edges, right? So then you can create the mesh. So in our case, just skip those parts and we will create the mesh directly. Alright, so in 2D I will be creating a Cora 3D in this case, and let's select the first node, the second node, the third node, and the fourth node. Alright, so let's name this one as wall 0. So the first wall has been created, and I'll be creating the second wall to create the elements, 2D elements, the correct type elements, and the first node, second, third, and the fourth node. Alright, and I'll name it as ID1. Okay, so this is the ground floor plan, right? So we are going to have the whole building right now. So we are going to use the translate function, and we are going to select all right into the Z direction. Okay, so we are going to copy. So the distance that we are going to use is about 16 feet, let's say. Let's make a preview. It seems nice, and we're going to have about 11 floor. Okay, let's make good alignment. Nice. And let's rename the mesh that will be created as the floor. Alright, so here you are. This is how you actually created the model. Okay, so we are ready to assign the boundary condition accordingly. Then first of all, I would like to make the element to front. So I would like to constrain the edge here, okay, so that there is not movement. So I'm going to freeze the direction of movement in the XYZ for both translational and the rotational. So what I'm going to do is I'm going to use the static heat analysis step, and we will be using the constraint. So in the constraint, I have a few conditions here. Alright, so this is where I allow for rotation. This is where I allow for translation. So I'm not going to allow for both the translation and rotation. I'm going to fix everything off, and I'm going to use this fix. Alright, so since that we are creating the nodes, I select the nodes. So the boundary condition can be also applied on the geometrical itself, right? So we are actually now dealing with the mesh element, the nodes. So with the nodes selected, you should be able to see the highlighted nodes, and we will select the whole nodes here, and let's see, and let's put it as a fixed boundary condition set. So all the information will be kept in the second tab, boundary condition fixed. So you can access to the value by right click and edit, and you can you can change the value at any time. So the second is we are going to apply the load, and we're going to have a few loads to be applied on the floor and the roof. And before we do that, we are going to apply the gravitational load. Alright, so let's plan what type of boundary condition set that we are going to apply. this is going to be my self weight. Oh, sorry, I should apply here, and let's make some sets. Self weight. The next is I'm going to have live load. Also, I'm going to apply the load on the floor, each of the floor, and I'm going to apply the load on the roof. So this is what I'm going to do. So first, I'm going to set up the load for the self weight, and this is gravitational load. We have negative z direction. Yes, this has been defined. Let's put it OK. So the load is being applied here. Right, so I'm going to apply the load on the floor. So what I'm going to do is I'm going to use a load on the beam here, the floor. Alright, so I'm going to select accordingly. Let's move it to front. Let's say, for instance, like, let's put a value. This is my floor live load. I'm gonna have minus 30, minus 30. The distribution, I'm gonna have a constant distribution. Okay, so I'm gonna have a constant distribution, and I'm gonna select the 1D element. Let's preview. Yeah. Well, let's turn off some others. Right, so this is the live load. Let's put it nice. Okay, so the live load is actually applied towards every floor. So we're gonna select each of the floor here, except the roof. And the last but not least, and let's make a preview. Okay, so this is my live load at the whole floor. Let's make apply. Okay, and the information is kept here. The next is I'm gonna apply on the beam as well, which is the dead load. Let's make this one on the floor. So I'm gonna apply on the floor. This is floor dead load, and we are gonna have 75 in my case. So I'm gonna apply on each of the floor, so we can turn off this if you don't want to see. So each of the floor will be applied with also the deload. Except for the roof. And let's make some preview. Here you are. And okay. So for our floor, we have two loads apply, which is the dead load and the line load, live load, sorry. And now we are going to focus on the roof top itself. We're going to eliminate as the roof as the live load. We're going to have a constant 25. So it's negative direction, it's always to be negative. So I'm going to store it to my roof here, and make sure you select this. Let's preview. Alright, so this is my roof. Apply. And the information is kept here. And I'm gonna have a second load, the dead load. So the value is 35 by minus 35. Again, select on the top. You're gonna have this roof, both, right? Okay, so we are ready to run the first analysis, and before we go into the seismic analysis. So make sure that we have correctly set up our mesh, the boundary condition, and as well as the load. So in this case, what I'm going to do, I'm going to perform a linear analysis case. So on the third tab here, analysis and result, the different type of cases will be kept into this QAP. All right. So one of the analysis, simple analysis that I'm going to do is I want to make sure that I have a connection between the nodes to nodes. I want also to make sure the boundary conditions, the constraint, the loads, and the self-weight has been applied correctly accordingly. So I have right click and created a linear static here. So I can edit and check all my setup. I will need to make sure the mesh I created has been involved into my analysis. And I have to ensure also the boundary condition has been selected accordingly to my analysis. So it seems nice, and let's right click and solve it. So we're going to expect some results. Yes, it solved it and we have the result. Okay, let's switch on everything and let's check. Yes, we have the result, linear static of displacement. This is amplified. We can make a real displacement. So this is the displacement, and we have the shell stress on the wall itself. Right, so it seems that the configuration for my boundary condition as well as the configuration of the mesh are correct, and it doesn't return with any error. So we can proceed for the next analysis, which is the seismic load analysis. Okay, let's start with some preparation of this response spectrum value that we need to excite for the vibration analysis. First of all, let's prepare some value in terms of the damping. We will go to LBC, the boundary condition setup, and we will look for these damping coefficients and model damping function. Okay, let's put the value of 0.2 function as 2%. So let's rename as 2% damping. Now we will prepare another set of function, which is the response spectrum function. So we will get some value in by using the design spectrum library. So within our library, we have different set of design spectrum. I'm going to use one of the set called KBS 2009, and I'm going to excite for 6 seconds in our case, and you have that. So once the value has been added, we will have to apply into our model. So let's align our model into the front view, and we will go back to this dynamics and response spectrum. So we will excite in the X direction with this value, and let's apply is X spectrum. Oops. Well, I have selected yes at, and let's apply. So the dynamic function is kept here, and let's apply the Y spectrum to be excited in the Y direction, the same thing. And next we will rename as Y spectrum. So there you are. So now we're going to create the analysis. We're going to create analysis for the spectrum analysis. Let's create the others, and let's look for the solver called response spectrum. Okay, let's put it as RS. Alright, so in our case, we will use the whole system to be excited under the response spectrum that we have already defined. First, I will have to initiate the load for the X spectrum, and let's rename by pressing F2. I will have to rename to X spectrum, and I'll create another new case called the Y spectrum, the subcase. Make sure you define your fixed boundary condition, and in the case as the Y spectrum. Alright, so we'll have to set up some other things like the model damping function, which initially we define at 2%, and we'll have some other parameters as well. In this case, let's put OK. So we'll go to each of the subcases. We will check the number of modes. Let's put it as 50 modes, and the same things as for the goes for this Y for the eigenvector, and let's OK. So we are ready for this calculation. Let's right click and solve it. So each of the case will be solved differently for the Y excitation and X excitation. So for the translation, you can see that the X excitation, and these are the distribution for nodal displacement or total movement. And if we excite in the Y direction, we have the total movement as well in this case. So I think that is all for my course. If you have any questions, you can drop me the email as below, and I will be happy to answer to any of your questions. All right. Okay. Thanks a lot, guys. So have a nice day, and I hope we could, to have communications soon. Thank you. Have a nice day to you. Bye bye.